Welcome to the 8th lecture in Modern Aspects of Nuclear Chemistry. This lecture is on forensics in nuclear applications. The readings for this lecture are from the book Nuclear Forensics Analysis, and the focus would be on chapters 2 through 5 in that textbook. The outline of this lecture includes isotopics. We're going to explore how actinide isotopics from nuclear material varies with reactor, including the type of reactor, irradiation time in that reactor, and the power of that reactor. In particular, we're going to focus on plutonium isotopes, but we'll also talk about transplutonium isotopes and how this provides information on material that's derived from these reactors. And these signatures we're going to discuss also for separations. When one produces nuclear material from a reactor, one is generally producing uranium, using uranium as a target, and producing isotopes from that uranium. The separations are going to leave behind certain indications on how the separation was performed and what type of material was separated. And finally, this lecture is going to end with a discussion on devices that are of interest for nuclear forensics. An overview of this lecture is shown here, where if one has a sample and one wants to understand something about the nuclear material to evaluate where the material was derived from and how it was intended to be used and how it could potentially be used after its interdiction, one could perform some radiochemical diagnostics and analysis, and these will provide information on the age of the material, something about the uranium-plutonium isotopics, trace elements, stable isotope information, and then you can also gain information about the morphology and properties of the material themselves. All this data is combined with non-nuclear material forensics, which is more traditional, where you would have chain of custody, fingerprints, DNA, etc. And this is interpreted based upon the material, expected properties, and expected uses. Plutonium isotopics provide excellent signatures for nuclear forensics applications. Plutonium can be produced in reactors, as we've already discussed through the capture on uranium-238 and subsequent decays of uranium-239, neptunium-239, plutonium-239. Two types of reactors that one may want to concern themselves with are light water reactors and CANDU reactors. Light water reactors use regular water as the coolant, and the uranium-235 is enriched in the fuel. So this will provide a signature that will transmit to the plutonium isotopics. The CANDU reactor, which stands for Canadian Deuterium Uranium Reactor, uses natural uranium with a deuterated water coolant. So it's D2O as the coolant. And as we'll show, the plutonium isotopics will be impacted by this fuel, which will provide a signature for where the origin of the plutonium resides. So plutonium can be formed in the core or even in a blanket of a reactor. Now, a blanket is generally material, such as uranium-238, that sits outside of the reactor area so that it can capture a neutron, form plutonium, and then one of the ideas was to take that plutonium and uranium and separate it and use it as fuel at a later stage. So there's fundamentally two areas in a reactor where plutonium can be made. Within the core, we have some different reactor types, and then in the blanket. And as we already discussed, plutonium-239 is formed from this neutron capture of uranium-238 that goes to uranium-239, neptunium-239, plutonium-239, and then the plutonium-239 can sit and become a target for the production of higher plutonium isotopes. So as plutonium-239 captures a neutron, it goes plutonium-240. That can capture a neutron, go to plutonium-241. There can also be some N-to-N reactions if you have fast neutrons, so you can also produce plutonium-238. If I have a fast neutron and it hits plutonium-239, it'll make plutonium-2 240, 2 neutrons coming out, plutonium-238. So from this we should get an idea that information related to the isotopic ratios of plutonium-238, plutonium-239, plutonium-240, and plutonium-241 can provide information about the reactor type and even the time that that material spent in the reactor. Continuing with plutonium-238, this isotope can also be produced through successive neutron captures on uranium-235. As we see here, uranium-235 can form uranium-236, relatively long-lived. Neutron capture on the 236 going to uranium-237, which would beta decay to neptunium-237. This neptunium-237 captures, going to neptunium-238, which then beta decays plutonium-238. This route, this neptunium to plutonium-238, is also the route for the production of plutonium-238 for thermoelectric uses. So a mixture of plutonium isotopics in fuel or blankets can act as a signature. The key is that plutonium-239 dominates at low burnups, and device plutonium has about 6% or less of plutonium-240. So these are key signatures that if one were to interdict plutonium material and it had relatively low amounts of plutonium-240, strong indication that it was used for a device. Relatively high amounts of plutonium-240 indicates that it could come from a typical commercial reactor. The isotopic distribution of plutonium is also influenced by neutron energy and its fluence. The energy of neutrons in a reactor can be influenced by the reactor operating temperature and the moderator. So signatures from the plutonium isotopics that are driven by the energy of the neutron can tell one about something about the reactor operating temperature and the moderator that was in that reactor. The fuel size also influences the distance between the neutron generation and the moderator. It can impart signatures into the plutonium isotopics. The fuel itself can influence the neutron spectrum. For instance, fuel that's high in uranium-235 will have a depletion of neutrons in the resonance region, since those neutron energies will be captured by the uranium-235 either for fission or for capture, depending upon what reaction. Now, we've already discussed plutonium-240 production, where one would want to limit that in reactions. And this is why a low fluence tends to indicate device plutonium, because as you make plutonium-239, you go through neptunium-239. If you have a high fluence, you may have a higher probability of capturing the neutron onto plutonium-239, creating neptunium-240, which will decay into plutonium-240. So this competition between capture on neptunium-239 and decay of neptunium-239 can have an indication for the plutonium-240 production. So as we see here, there's some figures below that show the range of plutonium isotopes that can be produced from going from uranium and neptunium to plutonium. And some of these bands include the decay of neptunium-238 from the capture on neptunium-237, and also our typical decay of uranium-239 going neptunium-239 to plutonium-239, but also the capture of plutonium-239 going to the 40 and producing plutonium-241, which is what we discussed up here. And of course, there's reactions that can occur that will remove plutonium that's produced, and these include neutron reactions onto the plutonium-239 that will induce fission, capture onto plutonium-239, which produces plutonium-240, that can then in turn produce plutonium-241, which undergoes beta decay to americium-241. Then if one goes all the way up to plutonium-243, you can get beta decay to americium-243. So this system has many components and is fairly complicated. A key signature that can be obtained from plutonium isotopics is an evaluation of the reactor type that was used to produce the plutonium. This is achieved by evaluating ratios with plutonium-240. For instance, the mass between the plutonium-240 and plutonium-239 can be evaluated. This is usually done with mass spectroscopy. And then the overall activity of plutonium isotopes, where the plutonium-238 is measured and plutonium-239-240 alpha spectroscopy data is provided. And a ratio of the 238 to the 239 plus the 240 is used. Plotting this is shown here, where the plutonium-238 divided by the plutonium-239 plus plutonium-240 activity is plotted against the 240 and 239 mass. What's shown here, and this is varied reactor types at 37.5 megawatts per ton, is shown that you can even evaluate differences between pressurized water reactors and boiling water reactors, although the difference isn't that great. However, it can be observed. And here's your nominal composition of weapons-grade plutonium. If you look at the plutonium-240 to 239 mass, over here would be weapons. Here would be more reactor conditions. But what is very evident is the differences between the light water reactor types and the heavy water reactor type, the CANDU, and then the differences further still between the reactor types and a blanket. So by looking at these activity and mass ratios for the plutonium isotopes, one can get an idea of the reactor that was used to produce the plutonium. The plutonium isotopics can also be used to determine the time that the sample sat in the reactor for the irradiation. And in this case, one uses the plutonium-239 concentration. So activities, or excuse me, atom amounts, atom ratios are provided against plutonium-239. As we see here, we have the 240-239 ratio, the 241-239 ratio, and the 242-239 ratio. In all these cases, as we go up in A, we see a decrease in the ratio as expected. But one sees a certain trend of radiation lengths from 10 days to approaching 1,000 days with the ratio. And this makes sense where you get a buildup of the heavier plutonium isotopes at longer radiation times. Plutonium-241 is time sensitive since it has a relatively short half-life. It can also provide information about the time since discharge. So this could be a key measurement. As you can see, it's very sensitive to the length of irradiation. Plus, it'll provide information based upon the decay plutonium-241 to americium-241. You can use that as a dating type signature for how long the material's been outside of the reactor. Reactor power can also be evaluated through plutonium isotopics. Again, mass, 242 to 239, and then the activity of the 238 divided by the 239 plus the plutonium-240 ratio. So this is a similar term to what we've evaluated before. This is a different mass, and we have to multiply it by 100 here, so we need rather sensitive instrumentation. But what we see for low reactor power, the variation is much greater for the activity ratios, not so much for the mass ratios. However, there's this regime where we go from 10 megawatts per ton all the way up to close to 1,000, or in this case just a couple hundred megawatts per ton. We certainly see a pronounced regime change where the determining ratios can, for both these routes, can provide two tools for determining reactor power. Again, reactor power can give you an idea of what was the reactor that was used to produce these plutonium samples. The transplutonium isotopes can also provide information on reactor power. This is true for americium-242, M-243, and curium-242 and 244. Then this is due to the relative decay of plutonium-241 and the formation of americium-241 from that decay. More americium-241 is available for reactions from longer times with a low flux. Weapons-grade plutonium is usually produced from 10 days to 2 years in an irradiation, so this gives one a window of which to explore these reactions. So, from the neutron reaction and beta decay of heavier plutonium isotopes, we get the plutonium-243 beta decay to the americium-243, and onto americium-243 there's neutron capture, americium-244 decaying to curium-244, that'll be one of our signatures, and then neutron capture onto americium-241, that's produced from the decay of the plutonium-241. This will produce americium-242 states, the ground state of this isotope decaying to curium-242. So the relative ratios of these isotopes are going to have a strong dependence upon the flux of the reactor.
An example of these isotopic ratios we've just discussed is shown here. So if one looks at the americium isotopic ratios, and this is for 6% 240 in a sample with plutonium, we see that this ratio decreases as the thermal power increases. Right, so we can go from 1 to 10 to 100 to 1,000 thermal megawatts per ton of reactor power. And from this, measuring this isotopic ratio of the americium isotopes provides a route for determining the reactor thermal power, which then tells us information related to where the reactor origin was for the production of the material. Same thing if we find plutonium, that is 6% 240, and the curium isotopic ratio is evaluated. We see a different trend between the 244 and the 240. We see that obviously as the thermal reactor power increases, we produce more curium-244 in relative terms, and this ratio goes up. And again, this is a mass ratio, so if one were to do activities, one would have to convert that to masses, or by a mass spec, one could perform these measurements. There's another example of a ratio that can be used, the curium-244 to americium-243 ratio, but we see that it's not as sensitive over the entire regime, over the entire energy regime. You only get some slight changes between 100 and 1,000 megawatt thermal per ton, so it's not as sensitive as a signature. The curium-242 can also be used to determine time since discharge, since it has a half-life of 163 days. We expect this to change compared to the other ratios because of the relative short half-life of the curium-242. Information on reprocessing techniques, routes, and methods can also be left behind in material that provides signatures for how the material was obtained. Generally speaking, in used fuel, you have about 500 grams of uranium per every gram of plutonium. So you obviously have a lot more uranium than plutonium. The enrichment level, if it's typical fuel, can be as high as 0.6%, and obviously this level depends upon the burnup. One can get information about reprocessing, particularly related to remote handling, criticality issues, and the limit of impurities. So this can give an idea of what sort of techniques were used to recover and obtain the plutonium. Some of these techniques can be ones that were mentioned before, such as solvent extraction, ion exchange, fluoride volatility, molten salt, or even something such as a precipitation method. And as an example, one could look at an initial table of long-lived fission products that are present at discharge from a reactor that's used to produce 1 gram of plutonium that contains 6% plutonium-240 by mass. So in other words, if I have 1 gram of plutonium that has this 6% 240 amount, just from the fission, I should have this, as the table shows here, these masses of the different fission products. and one could also look at the activity of these fission products. So some, obviously, something like neodymium 143, which is stable, will have no activity, whereas some, such as strontium-90, will have, for a gram of material produced, will have up to 10 to the 12th dpm of strontium-90. This doesn't mean that this material would be in the reactor, but it does say that you would have to separate these fission products from the plutonium. And now this may provide a signature, particularly for processes in which the separation is poor or incomplete. For solvent extraction processes, the main one that has been used historically for separation of plutonium is the Purex process. Within this process, zirconium, technetium, ruthenium are observable. The lanthanides, neptunium, and thorium are non-negligible, and neodymium is a key isotope. This is because there's differences in the natural levels of neodymium, the isotopic distribution of neodymium from nature, versus the isotopic distribution of neodymium due to fission. So one can determine information about neodymium if it comes from a fission process or if it comes from a natural process. And these are signatures of different reactor plants. Other solvent extraction methods include the Butex process, which uses a butyl carbidol solvent. This is a relatively poor separation of ruthenium. So material that has plutonium that has a relatively large amount of ruthenium 106 in it will have an indication that it came from the Butex process, or a hexone process, which is a separation with methyl isobutyl ketone as a solvent. Again, ruthenium can be a signature here, as for and also an additional zirconium, niobium, and cerium. So as an example, 1 gram of plutonium has about 1,000 dpm zirconium-93 in it if it was purified by the hexone process. And this is a review of some of the separation routes that are used in solvent extraction on an industrial process, where you could have mixer settlers, so where the solvent and aqueous phase are mixed, they phase separate, and then one could pull off a certain phase that contains the actinides, and then the fission products go another route. A contactor, a centrifugal contactor, where you have an inlet for the solvent, an inlet for the aqueous feed. The materials are mixed, separated in the contactor, and then the solvent that's loaded with your target material, for instance, if it was a Purex process, the uranium and plutonium would be going into the organic phase. Or pulsed column, where an aqueous phase is fed into the top, migrates down to the bottom of an organic containing column. The separation occurs during the migration down, and then one could pull off the organic phase, which is then loaded with, in this case, it was a Purex process, uranium and plutonium. Similar to what we discussed about the fission products, the transuranic isotopes can also be produced during the production of plutonium, and the materials can also provide signatures, as we've previously discussed. So as an example, if one produces 1 gram of plutonium that is 6% by mass plutonium-240, one can expect the isotopes of neptunium, americium, and curium to be present. Their relative masses can be listed here, so per gram of plutonium produced, you would expect these masses of the other isotopes to be produced. So some, for instance, curium-244, we're talking on the order of nanograms being produced, relatively small amount. But since the half-lives are short, the activity is listed here in decays per minute, can vary on the order of 10 to the 6th to 10 to the 9th per gram of material. That's unseparated material. So obviously when the material is treated and plutonium purified, you get lower amounts of these activity of these isotopes. However, incomplete separation provides a route for determining signatures in this material. During the treatment and reprocessing of radioactive material, signatures can be introduced due to the radiation itself. For instance, radiation effects can include polymerization of organic phases, degradation of the ligand, for instance with tributyl phosphate, One can form di, mono, or phosphoric acid. So think about you're just breaking down that organic molecule. And you can also, depending upon what's present with the TBP process, or TBP ligand in the Purex process, you can form N-butanol and nitrobutane. So the influence of radiation would tell you something about, if you were to obtain even the organic material, it can tell you something about how much material had been processed through that organic solvent. This can also influence extraction behavior and has some limitations on extraction efficiency, and a range of organic compounds as shown here can be formed. So this would vary the separation process and could be a route for the introduction of material that is not the target isotope into the final product. So for instance, as shown here, we can look at neodymium isotopes, and we can compare those. What we're looking at here is neodymium isotopic ratio by mass for production of neodymium-143 versus the total plutonium production. Again, we're focusing on a 6% plutonium-240 as a function of a power level in a graphite moderated reactor. So a graphite, naturally uranium fueled graphite moderated reactor has, as it says, natural uranium as the fuel, and the moderator, as opposed to being water or deuterium, is graphite. Again, that'll provide some different signatures. But what we want to show here is that if we look at this ratio of the different neodymium isotopes, or the neodymium-143 plutonium total, that ratio varies a little bit depending upon the power level of the reactor. We're just going up by orders of magnitude. But we do see that there are some isotopic ratios which could be measured. The sensitivity would be difficult. For instance, over this entire 2 orders of magnitude range, the isotopic ratio between the neodymium-150 and the neodymium-143 doesn't vary much. But what one could see, if we looked at the ratio of the neodymium, is we see information related to the isotopic ratio due to the reactor and the isotopic ratio due to natural neodymium. And the reason that this is important is that it tells us something about the nature of the material that was used in the reprocessing. So for instance, if one has nitric acid that has trace neodymium in it, that nitric acid would provide a signature in the separation. So you would have a mixture of natural neodymium isotopic ratios and this neodymium isotopic ratio that's driven by the fission process. And the fact that we don't have a large change is actually something one could exploit, because it can give us an idea of where material is coming from that's used in the actual separation process itself, due to the fact that this natural neodymium isotopic ratio is indicative of the material prior to its introduction into contamination, into treating a material that's gone through a reactor. We're going to conclude this lecture with a discussion of some very general signatures and devices and how those are used for nuclear forensics. Generally speaking, a device would like to have the highest neutron multiplication factor. So this increases the neutrons and fissions from one generation to the next. Designs of devices try to maximize this, and one of the terms that's used in this is a generation time, and it's the average time between a neutron release and a capture. So think about it, if you look at a typical diagram, you have one generation fissioning, those neutrons go off, fission something else. That generation is called a shake, and each shake produces about has a neutron energy of about 1 MeV and has a time period of about 10 nanoseconds. 50 to 60 shakes produce about 1 kiloton of fission. This is about half of a microsecond, and this is an exponential. This is an exponential type of reaction. So most of the energy is just from the last few generations. The behavior of neutrons in devices is important and provides a route for understanding signatures. Generally speaking, a device would have something that would reflect neutrons back into the reaction area, so you have some sort of reflector. The fission spectrums drive the NF reactions. They're not; these neutrons are not thermalized, so that's an important difference between a device and a reactor. Remember that these things are traveling the neutrons have an energy of about 1 MeV in a device. The cross sections for the vast neutrons are orders of magnitude lower than thermal neutrons. Remember when we talked about the fission process for uranium-235, we saw that the thermal neutrons had a much larger cross section. So within material, you tend to have limiting non-fissile isotopes that provide signatures. We've already discussed less than 7% plutonium-240. If it's uranium, it's more than 20% uranium-235, and it's if you had uranium-233, you'd have relatively low amounts of uranium-232 on the order of 10 ppm, just because the daughter of uranium-232, there's one of the chain products produces a very intense gamma. Some other signatures that you would see with plutonium material would that you would not want low Z material in the plutonium. These react with neutrons. It lowers the overall density and it moderates the neutrons. So plutonium device isotopics in non-metal form indicate storage or starting material. The metal is the final form that's desired in the device, and often the material would be alloys. So these are other signatures. In plutonium, gallium is often used as an alloying material, and uranium, niobium is used. So if one were to find material that was not metallic but had the correct isotopics, one could conclude that it was a storage or preparation stage material that might be used for a device. If one were to find metal, one can conclude that it's definitely on the route to being a device. And then if one had alloyed systems or material that had contained the alloys, so plutonium gallium alloy and a uranium niobium alloy, that would be even a closer indication that there's of a signature that this is a material that is useful for a device. Now, there's also nuclear forensics related to post-detonation analysis, where one could evaluate debris from a nuclear event in which the function and the source of the fissions would be identifiable. Something about the energy, something about the number of neutrons. You can get information about the yield, so how effective this device consumed its fuel. You can also understand something about the energy of the neutrons from the number of N-to-N reactions that were made. So faster neutrons, meaning that there will be more N-to-N type reactions. And this is an indication, you can also get indications about the initial isotopic composition, so that the neutron energy influences the fission product distribution. The type of target material, whether it's uranium and plutonium, will have different fission product distributions. So looking at the fission products can give you information about the composition of the fuel of a device. In this lecture, we reviewed signatures that are germane to nuclear forensics, particularly isotopic ratios, plutonium isotopic ratios, americium isotopic ratios, curium isotopic ratios are particularly useful in determining the origin of the of plutonium-containing material, the length of an irradiation, the type of reactor in which it was irradiated in. We also discussed some general overviews of devices and how those are germane to nuclear forensic signatures. So as an example, some questions you should be able to answer. What signatures are available from plutonium isotopics? Well, the plutonium isotopic ratio can give very valuable information about where the plutonium was generated. If one evaluates the plutonium-238 to 239 240 activity divided by the 240 to 239 mass, one can find out if the plutonium came from a light water reactor, either a pressurized water reactor or boiling water reactor, a heavy water moderated natural fueled reactor, a CANDU, or a blanket, which is uranium that's outside of the main reactor zone, that's used for capture of uranium to plutonium. This, if one were to have a look at some obtained plutonium material, evaluate these isotopic by mass and activity ratios, see where it lies, one could first of all determine if it's designed for weapons use by the nominal 6% plutonium-240 composition, and then look at where it came from. So what type of reactor. And this is important because if it came from a CANDU, you can identify the locations. There are a limited number of CANDUs that are available for producing this material. Or a blanket type material would tell you what sort of reactor design. What material can be alloyed with plutonium? Well, if one goes back to the plutonium lecture, you'd see that there's a host of material that can be alloyed with plutonium. But for forensics applications, it would be gallium that's used for an alloy of plutonium. And why do neodymium fission products, isotopics, differ than the natural? This is primarily driven from neodymium-142. Neodymium-142 is 27.2% of natural neodymium, but it is not produced in fission, doesn't have a fission yield. So the fission product neodymium would not show this isotope, and you would be able to determine by looking at isotopic ratios of neodymium whether its nature was from a reactor or from natural. And this would mean that if there was natural neodymium in a component of a process, so for instance, if there was a natural amount of neodymium and nitric acid that was used in the Purex process and that got introduced into a signature, one could evaluate potentially where this nitric acid came from, or at least get an idea of the broad source origin of that material. Not only can isotopic information give you data related to what type of reactor produced the material of question, but you can also get an idea of how long that material sat in the reactor. So what kind of information can you use to determine material radiation time? Well, the plutonium isotopes provide great information on that. You'll see an increase in heavier plutonium isotopes with time. So plutonium-239 as it sits in a reactor, 1, it's fissioning, and 2, it's capturing. Plutonium-240, plutonium-241, etc. So the relative concentration of plutonium-239 decreases with time. And what one can do is evaluate the atom ratio of different plutonium isotopics. Everything normalized to the 239. The values continually increase as the length of irradiation increases. So the atom ratio can go anywhere from a number greater than 0.1 to values well under 1 times 10 to the negative 5. The other information that you can get from this is actually related to how long the plutonium has been out of the reactor. And this has to do with the plutonium-241 isotopes information. This has a relatively short half-life, the plutonium-241 isotope. So if one were to have a sample and identify the irradiation time from the 240 to 239 ratio, 242 to 239 ratio, you would have 2 data points that would indicate a time. You could evaluate the 241 to 239 ratio. Any decrease in the relative amount of plutonium-241 can be identified. The isotope plutonium-241 is a 14.29 year half-life. So by taking the data points, which would give you the irradiation dates from the 240, 239, 242, 239 ratio, you'd be able to determine what should have been the plutonium-241, 239 ratio at the end of the irradiation. You could measure what it is today, and one could use the half-life of 14.29 years, to determine the length of time it's been out of the reactor. Now you can imagine that this is only sensitive for samples that have been out for a time period that's on the order of a half-life. Other information that one can get is related to fission products and what sort of signatures can they provide. Well, for separations, one can look at these fission products that are listed here. They're relatively, some of them are relatively short-lived, some are relatively long-lived. So this gives you a range of what sort of time span one can use to evaluate material. One of the isotopes is even stable, the neodymium isotope. And these are isotopes, fission product isotopes, that are present in discharge in a reactor fuel used to produce 1 gram of plutonium. So if you had a 1 gram sample, for every 1 gram sample, there would be this sort of activity of these isotopes. And what these isotopes provide is a route to evaluate different types of separations that were used in the production and separation of the plutonium. The Purex process has certain signatures for the fission products, and the redox process and the hexone process, as we discussed in the lecture, have different signatures compared to the tributyl-phosphate-based Purex process. So from this, one can get an understanding of not only how the plutonium was produced, what type of reactor, how long it sat in that reactor, but also what chemical method was used to purify it.
You've completed the 8th lecture on nuclear forensics for modern aspects of nuclear chemistry. When you've completed this lecture, please comment on the blog and respond to PDF quiz number 8.